Welcome back, Mindsetters. I hope you're enjoying the show. And now Zelda has joined us for a short while, and we're going to be moving on to November. I think it's November 2010, Paper 2, Question 8.
Question 8,
Yeah.
absolutely. Good afternoon, Mindsetters. It's a privilege to be with all of you this afternoon. We're going to look at an electrochemistry question. Now, this section, you must remember, although we do redox reactions, and that's electrochemistry, it also links up with that entire section that we do on the battery industry. So where we work with the chloroalkali industry and there are batteries over there, this entire section links up with that. So we need to make sure that we understand the whole concept behind redox reactions when we go through this. Now, I've chosen this specific question because it approaches the redox reaction from a slightly different angle. We generally give you questions where we go and we go and calculate the E naught of the cell, so the EMF of the cell. In this specific question, they've gone and they've given you the EMF of the cell, and we need to go and find the unknown electrode in our cell. So let's have a look at this specific question over here.
Let's get on to it.
Yeah. Now, they tell us that the cell notation of a standard galvanic or voltaic cell contains an unknown metal. Let's just get a pen over there. An unknown metal with an electrode X, which is shown below. So if we go and we look over here, this is the notation that they've given us. So we can see here's the one side of my cell with my unknown electrode. It's indicated as an X. And on the other side of the cell, we work with lead. Now, the first question they ask us is to name the component of the cell that is represented by the double vertical lines. So if we go and we look over here, there's the double vertical lines that they're referring to. Now, if you remember, if you go and look at your cell as we work in the classroom, these cells have a salt bridge that connects the left-hand side to the right-hand side. Now, that salt bridge allows for the movement of your charged ions between the two solutions. And in this specific cell notation over here, these double vertical lines that they're asking us about over here would represent the salt bridge. So it represents the salt bridge of the cell. Okay, let's go look at question 8.2. Now, from there, they go over and they tell us that we need to state two standard conditions that are applicable to this specific lead half cell. Now, remember, when we work with standard conditions, those refer to conditions that are kept standard in all reactions that we do for these specific experiments. And because we are working over here with a reaction where we have liquids that are solutions, there are two standard conditions that we look at. First of all, we need to go and look at the concentration. Remember that the square brackets that we use over there represent concentration, or you could write it out as the concentration of the solution of the electrolyte is equal to 1 mole per cubic decimeter. All right, so that is the known concentration that we have over there. Now, the next thing that will affect this specific reaction would be the temperature at which the reaction takes place. So the temperature at which we work over here is room temperature, and for us in science, that room temperature would be a temperature of 25 degrees Celsius. And we would also accept it if you tell us that it is 298 degrees Kelvin. Okay, so either one of those two, the one is your SI unit for temperature, and the other one is a normal temperature gauge that we use in South Africa. Either one of those would be accepted in this specific instance.
I was wondering if I could ask a question. Yeah. Nisa from Facebook, I think it's a girl, she's got pretty swans as her picture. She said, please could we go through the anode and cathode and how you get them? She always gets confused between the two.
All right, it's coming up a little bit later. I think it's question 4 on this one.
That always happens. They always know when the questions are going to come up. So
yeah,
there you go.
Preempt it, so
yeah.
we'll get there.
Okay,
all right.
Keep watching.
Okay, question 8.3. They want us to go and identify the oxidizing agent in the above cell. Now remember, there's a whole list of acronyms that we can use to help us remember which one is the oxidizing agent, which one is the reducing agent, or with which electrode do we have oxidation, or at which electrode do we find reduction. key thing to remember over here is your oxidizing agent is the one that undergoes reduction, and your reducing agent is the one that undergoes oxidation. So if we look at this specific cell, at this notation that we have over here, remember, if it is going to lose electrons, it is going to go and the positive charge would become bigger. So if you look over here, you will notice that the oxidation number for my unknown element there is 0, and it goes to a +3. Over here it goes from +2 to a 0 oxidation number. Now if it has gone from a 0 to a more positive value, then we know it has lost electrons. Remember, your electrons have negative charges. So if I lose something negative, I become more positive. In this case, my element has lost electrons, and therefore it gains a more positive charge. So on this side, where electrons were lost, it loses electrons, and therefore it becomes oxidized. Right, I like to use the acronym LEO says GER. Other people will use different ones. There's oil rig and all of them. Okay, but the loss of electrons, oxidation occurred over there. On this side, it went from a positive +2 to a 0 oxidation number, which tells us that we gained electrons. And when electrons are gained, it becomes reduced. So that's where I get my LEO says GER from. Okay, that acronym that I use over here. So if I now bring it into the question asks us to identify the oxidizing agent. So remember what I said, the oxidizing agent would be the one that undergoes reduction. And the one that undergoes reduction in this case would be the lead ions. So your answer over here would be it is the lead ions. Or we would also accept it if you just tell us that it's Pb2+ as your lead ion over there. Right, any one of those two acceptable? Let's look at question 8.4. All right, now they tell us that the initial reading on a voltmeter connected across the electrodes is given to us as 0 or 1,53 volts. And they want us to identify the unknown metal. Now remember, when you have a spontaneous reaction, energy is given off. It's an exothermic reaction. And in this case, the energy that is given off can be measured in terms of the potential difference or the electricity that we find over there. And the apparatus that we use to measure the electricity is the voltmeter. So that's why they give us a voltmeter reading over here. So to go into that, remember in your formula sheet, you will find 3 different formulas that will help you to go and calculate your potential difference. You go and use the one that is applicable to your side. Now there's the one for oxidation, what did I just say? Agent 007.
You know, it happens to teachers too. Do you know how hot it is today as well, guys? It's so hot in the studio.
My brain is melting like a soft serve.
I'm telling you, don't talk about soft serve. I want one of those.
All right, so you can look at your oxidizing agent or your reducing agent. I like to work with a cathode or the anode. And in this case, remember that if this is where my reduction occurs, that is going to be my cathode, because I look at my red cat. So let's just write in the right order. Reduction takes place at my cathode. So if I'm going to use this in my calculation, my cathode is going to be that side. So I'm going to look at the following formula. The E0 of my cell is equal to the E0 of my cathode minus the E0 of my anode. And they told us in the beginning over here that the potential difference for my cell is 1,53 volts. Now, if you go and you look at your standard table, your standard reduction potential table over there, depending on what your teacher taught you at school, you would either use table 4A or 4B. And you go and on that table, go and look for lead. So you're going to look for lead. You're going to read it from the side where it's lead Pb2+. All the way through to lead as Pb, and the value that you're going to have over there is going to be negative 0,13. Use the brackets, it just helps you to keep everything together with the symbols that we have, and then we don't know the potential difference over here for this specific anode. So we're going to do our calculation over there. Now, if you bring the negative 0,13 across, it's going to become positive. So it's 1,53 over here, minus becomes a plus, and that is going to be your 0,13, and that's going to be your E naught of your anode that we calculate on this side. Now, if you go and you calculate the E naught for your anode, you see that your E naught for the anode works out to be a fantastic 1,66 volts over there. And that's a negative value, sorry. Where did I go wrong? There's my negative that I need to divide. So it's still negative over there. Let's just put it down. Okay, so let's just go through that again. I might have confused some of you. When I bring my 0,13 across, it becomes positive 0,13. But on this side, there's still a negative in front of my anode, so I need to keep that negative. And afterwards, when I divide to get this positive, it becomes a positive, and my answer there takes on a negative 1,66. All right, just be careful of your signs and your symbols over there. As you can see, just as easy as I make the mistake, it's possible for you to make the mistake. So remember, always when you're busy with a calculation, afterwards, go through, make sure that you followed the correct procedure for your BODMAS to transfer the signs and everything as you go across in your calculations. Let's look at question 8.5. Now, question 8.5 asks us to write down the balanced equation or the net overall reaction that takes place in this specific cell. Now, this is after you've done your oxidation half reaction, your reduction half reaction, where you get to your net cell. Now, in this specific question, they didn't ask us to go and do the oxidation half reaction, the reduction half reaction beforehand. And you'll see that it's only worth 3 marks over here. Remember, go look at your mark allocation to determine what exactly they're asking you. If they're asking you, if they're asking you a question and the mark allocation is 5, and you go and write down 1 sentence, it's impossible for us to give you 5 marks for 1 sentence. So always refer back to your mark allocation so that you know exactly what you need to work with. Okay, so they want the balanced equation. Very important that you go and you balance it for the overall. Can we just go back to 8.4? Because we've now calculated over here what the value was, all right? But we still don't know what X is. I kind of like jumped ahead. So once you've calculated the potential difference over here, you're going to go back to your standard potential table. So you're going to go back to table 4A or 4B, depending on what you've been using at school. And then if you go on your left-hand side, your right-hand side, my left-hand side, you're going to go down the table, and where you find the negative 1,66, you're going to identify the element or the metal that you're working with over there, and we see that substance X, in this case, worked out to be aluminium, because aluminium has the potential difference over there of negative 1,66 volts. So now that we know what our unknown ion is, we know which element is going to be at our anode, and we're going to go and write the oxidation half reactions. So let's look at question 8.5 now, where they ask us to go and write the net equation. Now, for the net equation, remember that's the overall sum between the oxidation and the reduction half reaction. So you're going to start off with your aluminium. Now look at what we have over here. You will see that on this side I start off with X as a solid, and we've now identified X to be aluminium. So you're going to start off with aluminium in the solid phase. It is going to react with my lead that I have. It's the first one that you see after the double line. Remember, the double line over here indicates your salt bridge. So it starts off with X and it starts off with your lead over there. So it's going to react with your Pb2+. And this is in an aqueous solution because it's dissolved in liquid or in water. And then the second part of your reaction is where your aluminium over here is now turned into your aluminium 3+, so it's the ion that it's formed. So it's going to be Al3+ over here, and it's gone from the solid phase over into the aqueous solution. So when the atom loses its electrons, it turns into an ion, and that ion is in the solution, and that's why you indicate over there AQ as an aqueous solution. and then your lead has moved from being a PB2 plus into PB, and you write it down over there, and this is now in the solid phase. Now all we need to do is make sure that it is balanced. As you can see over here, your aluminium has got a 3 plus charge over there, and over here I've got lead which has got a 3 plus charge, and I need to balance that out. Okay, so I'm going to use I'm going to have 2 aluminiums, and I'm going to have over here 3 lead, and on this side I will have 2 aluminiums again and 3 lead. Now if you're a little confused as to where I get that from, let's just very quickly remember this is our net equation. This is just for you to understand a little bit better where I'm getting it from. If you go and you look at your oxidation half reaction, the oxidation half reaction is going to be where your aluminium is. So your aluminium will go and it will lose electrons. So when it loses the electrons, it is going to turn into your aluminium over here and the electrons that it's lost. So there's 3 electrons. And on your reduction side, you're going to have the lead, which is going to gain the electrons, and it will turn into PB metal. Now remember, when you need to balance this out, the idea is to get rid of the electrons. You must balance those electrons out completely. You can't have electrons in your net equation. And to do that, we need to go and find common multiples. Now between 2 and 3, your common multiple would be 6, and that's why this entire reaction, I go and I multiply that by 2, and this entire reaction, I go and I multiply by 3. And that's where I get the 2 in front of my aluminium and the 2 in front of my aluminium. And when I multiply this by 3, that's where I get the 3 from for each one of those. So although the question don't ask you for an oxidation reduction half reaction, there's nothing that says that you can't do it. Go do that oxidation half reaction, the reduction half reaction, get them to balance, and then go and write your net equation over there. You're not going to lose marks for adding this specific section in to your answer for this question. Okay.
Zelda, I have a question from Alan. He wants to know, what would the value of the reading on the voltmeter when the cell reaction has reached equilibrium? He said it's the same question you're working on now.
Okay, so coming up maybe later.
Could be.
Yeah, there we go, question 8.6.
And then also McBerry Evans keeps asking why you keep looking to your left, but I suppose because it's I'm here. Because I'm here.
Because Anna's over here. I'm kind of like distracted by Facebook over here on this side.
Don't get distracted. You do
networks.
I'll do my job, you do yours, and you guys keep letting
Sending
me
in
know
questions.
if there's anything that Zelda can help clear up. I'm right here. I give her a little tap on the shoulder, and it's that quick.
Absolutely.
Okay.
Okay. So 8.6, to answer that question, how will the initial voltmeter reading be affected if the concentration of your electrolyte is increased? Now remember, if your electrolyte, which in this case was the aluminium, undergoes oxidation, it produces electrons. The electrons are released, so they go into the solution. What is electricity? Electricity is movement of electron. It's those charged particles that move around. So if I increase the concentration of my aluminium solution, then all of a sudden you're going to find that more electrons will be released, and it's going to get the cell to produce more potential difference or more voltage in this case. So if you go and you look over here, they want us to only indicate whether it is going to increase, decrease, or remain the same. Now, by increasing the concentration of the electrolyte over here, I'm increasing that part. So let's just open that up so you can see what I'm talking about. You're increasing this, the concentration over there. So suddenly there aren't enough electrons to move around from the other side. So you will notice that there is a decrease in your voltmeter reading. Because if you go and you look at your reaction, this side is going to lose the electrons, but it gets its electrons from the solid. And this side is going to gain the electrons, and it's going to go from the aqueous solution phase into the solid phase. But now I'm increasing this part. That doesn't mean that more electrons will be released from here. And because I'm increasing this part, which has no effect on the losing of my electrons, I find that my voltmeter reading actually decreases. So over here, your answer would be decrease over here. Now, there was a question earlier on Facebook where a learner asked, do I write increase, decrease or remain the same, or do I compare the two? If the question asks you to say increase, decrease, or remain the same, then that's what we want you to write. Only one of those three options. But what I've noticed in the last couple of exams, they ask you to explain why. So it's no longer just going saying, okay, eeny, meeny, miny, mo, choose one of the three and hopefully that's the right answer. If you choose the answer, you must be able to explain to us why you chose the answer. So we're not testing your guessing abilities anymore. We're now also testing whether you understand the question. All right. So in this case, if they had asked you to explain why, it would be because increasing the concentration does not increase the number of electrons that are emitted for this calculation. The last question, 8.7, they want to know the value of the reading on the voltmeter when the cell has reached equilibrium. Okay, now remember, what is equilibrium? Equilibrium is when two things are balanced. And just imagine you're sitting on a seesaw. You're sitting on one side and your best friend is sitting on the other side. If the seesaw is perfectly balanced, it means that there is zero difference between the two. And the same thing happens with a cell. If it has reached equilibrium, there is no difference between the one side of my cell and the other side of the cell. So if there is no difference between the two, there would be no reason for the electrons to move around anymore. Okay, they always go from a higher point to a lower point. So if they're equal, there's no reason for them to move around anymore. And then you won't register a voltmeter reading. So in this case, where they ask us to go and write the value of the reading on the voltmeter, it is going to be 0 volts. Because there is nothing to register. There's no movement of electrons taking place anymore. Okay, that's then question 8. Anything else over there from your side?
Well, Trince or Trincy, she wants to know, okay, it sounds easy, she says, with cell notations, does anode always have to be on the left?
Yes, we try and keep it, your anodes on the left-hand side, cathodes on the right-hand side. I'll always teach my kids in school, it's the way the alphabet goes. A is before C in the alphabet, and we read from left to right, so A is on your left-hand side, C is on your right-hand side. I find that I myself quite often use letters of the alphabet or orders in that way to remember things. For instance, with organic chemistry, I know I'm going over into a section we've done.
These things help.
For your single bonds, you have alkanes, and A is the first vowel of the alphabet, so it's a single bond. Alkene is the second vowel in the alphabet, and an alkene is your double bond. All right, and then in the if you go into the Afrikaans language, we sometimes use the Y as a vowel. For our language, and that's the very last one, so the very last type of bond would be a triple bond. And that's how I teach it to my children, is to use the vowels in the alphabet to remember which family it belongs to.
Nice
and it's
easy.
Just short little hints like that.
Yeah. And I just want to say, it's so fantastic on the page. Students, mind-setters are helping each other out on the page.
I've noticed that, and I find it amazing that the kids, jump in, listen, I see you don't understand this question, this is what we do. And that's what it's all about.
And Zelda's a fellow Facebooker like John. Like every now and then you see John posting comments, but sometimes Zelda will do as well. So you never know, she might write back to your questions later. Let's see how much time she has on her lovely Sunday afternoon. Fantastic.
Right, anything else?
Let me just have a quick look. Let me have a look, and you know what? I'll tell you after the ad break. Maybe we can discuss a few things, a few comments.
Fantastic.
Yeah, see you after the ad break.